Let's come up with the Taylor series for cosine of x and also the interval of convergence for cosine of x. So ideally this would be a Taylor series we would have memorized, but if we need to derive it, we'll look when at x equals 0 will be where we are centered. And so we need to consider the derivative of the cosine of x, which is negative sine of x. The second derivative is negative cosine of x. The third derivative is sine of x. The fourth derivative is cosine of x, and we'll go maybe one more term. The fifth derivative is negative sine of x. Take that back. Let's go even one more term. The sixth derivative is negative cosine of x. So we know we can already recognize that things are going to be flip-flopping back and forth. The value of the function at 0, well, the cosine of 0 is 1. The value of the derivative at 0 is 0. The value of the second derivative at 0 would be negative 1, and it's just going to keep working this way all the way down. So we've got the function's value and the derivative and second derivative and so on and so forth. So as long as we know the pattern for Taylor series, we can derive this, and recall that in general your Taylor series can be constructed from the function's value at a, which is the point where you're being centered, plus f prime of a over 1 factorial times x minus a to the first, plus f, or the second derivative, f double prime at a over 2 factorial times x minus a squared. And again, a is the point where you're centered, plus the value of the third derivative at a over 3 factorial times x minus a cubed. And this pattern just continues for a Taylor series in general. So what we're saying is that the cosine of x is approximately equal to 1, that's f of 0, plus 0 over 1 factorial times x to the first, minus 1 over 2 factorial times x squared, plus 0 over 3 factorial times x cubed, plus 1 over 4 factorial times x to the fourth, plus 0 over 5 factorial times x to the fifth, minus 1 over 6 factorial times x to the sixth. And this will just keep going. And hopefully you can see that there's a pattern in what's happening here, which leads us to our nth term. And our nth term in this case, well, it's an alternating series. So we need a negative 1 in there. And we want the even powered terms to be negative. And this will happen when we have negative 1 to the n power. We only want the even powers on x, so this would be x to the 2n over 2n factorial. And make sure you can see why this is a good expression for the nth term. And it might not be obvious now, but hopefully it'll stand out once we simplify. So then if we simplify this, the cosine of x can be approximated by 1 minus 1/2 x squared plus, well, 4 factorial is 24, so 1 over 24 x to the 4th, and 6 factorial is 720, so minus 1 over 720 x to the 6th. And we can take this out as far as we need to go, and the nth term of our entire series is negative 1 to the n times x to the 2n, because we only want the even powers, over 2n factorial. This is our series. Now, to verify the interval of convergence, we can use the ratio test. And the ratio test is the limit as n goes to infinity of the ratio between our a to the n plus 1 term over our a to the n term. Right? In a sense, we're using inductive reasoning. Right? We're looking at the ratio between a term and the one after it. So if we set this up, this limit has to be equal to the limit as n goes to infinity. Well, a to the n plus 1, everywhere that there's an n in my nth term, I'm going to put n plus 1 in. So this would be negative 1 to the n plus 1, x to the 2n plus 2 over 2n plus 2 factorial. And this will be divided by the nth term, or multiplied by the reciprocal of the nth term. So this would be 2n factorial over negative 1 to the n times x to the 2n. And this can be simplified so that our limit as n goes to infinity would be equal to negative 1 times x squared over 2n plus 1 times 2n plus 2. And if we break this up a little bit more, just to make it hopefully easier to see, the limit as n goes to infinity, if we looked at each individual piece, the absolute value of negative 1 is just going to be 1. That part becomes insignificant. And we want to look at 1 over 2n plus 1 times 2n plus 2 times the absolute value of x squared, which will always be positive for all values of x. If you square it, it'll be positive value. So that's why it's just times x squared. Now our limit as n goes to infinity of 1 over 2n plus 1 times 2n plus 2 will be 0. Right? Because the denominator is getting large, while the numerator is staying at 1. So this limit is 0. So we end up with 0 times x squared. And for all values of x, this is equal to 0. Now by the ratio test, this thing will converge whenever the limit is less than 1. That's when convergence occurs for those values of x where the limit is less than 1. In this case, for all values of x, the limit is 0, which is why we can conclude that the interval of convergence is negative infinity to infinity, because for any value of x we use, the limit will be 0.